A very, very good afternoon to all of you. First of all, I want to thank Vinay for, as I said to him, taking the risk of inviting an engineer to CCMB. I also want to start with an apology, which is not a good way to start a presentation. This is the first time that I've been at CCMB. I've spent 27 years in CSIR, and I've come to your neighboring institute very large number of times. But this is the first time I'm in CCMB. But in the last 2 hours that I've been here, I've really seen a magical confluence of art and science blended together. I just came out of the microscopy facility, the fantastic microscopy facility, and I see wonderful paintings on outside and equally wonderful images inside the microscopy facility. So it's really, truly very unique to see science blended with art to such an intricate level. Real privilege for me. I feel so proud to be here on the Founders Day. I've heard so many things about Dr. Bhargav. He is a tall figure, and we had at NCL people like Dr. Mashelkar who were connected with such tall people in India, and I've heard from him, I've heard from others about Dr. Bhargav a lot. So it's a real privilege for me to be here on the Founders Day to give this talk. I worked on many topics after joining NCL. A lot of it was very deep science based. It was a mix of physics and engineering, mostly on macromolecules. But sometime in 2009, I completely switched and went into an area that I had known nothing about. And it was definitely not my area of expertise. To some extent, I was pulled into this area, but eventually I got fascinated about it. For the simple reason that it was a very forward-looking area, the one that I'm going to talk about, in 2009. And I took it up as a challenge to get into a new area, something that we hedged our bets on that might become important to India. So green hydrogen is an area that I entered into as a complete novice, didn't know anything about it. But today I can say that to some extent at least I can come and give a founder's talk in CCMB. So Vinay, thank you so much for inviting me over here. So I'm going to talk about the role of green hydrogen in what we call India's future of energy transition that will hopefully lead us to not just clean energy but also energy security. I'm going to keep this a very generic talk, so there's a lot of information in it. I'm not going to talk much about science that we have done in this area. Honestly, I didn't know how to pitch this, okay, and I didn't even have time to prepare a very specific talk about this. So it's mostly very generic and mostly informational, but hopefully it is interesting. Okay, so let me start by saying where we are today in terms of our energy needs. Why is it so important, and what do we look as the future of a country that is growing? It's a very aspirational country. So we are talking of, I'm sure you've heard, the GDP growth of the country, one of the fastest and the most exciting GDP growths in a democratic country. All these terms are important, and we are looking at hitting about $5 trillion. And if we go at the rate at which we are growing, we might even hit $8 trillion by 2030. And by the time the country reaches 100 years of its independence, we are looking at a $30 trillion economy. Now, this is signs of a nation going from a developing status to a developed status. Now, GDP growth of a country doesn't happen without energy. You need energy to fuel the economic growth of the country. What is happening today is we are importing a huge amount of carbon atoms in the form of fossil fuels. We import gas, we import coal, we import oil, and we burn all of it to produce our energy. And that energy is what is fueling the growth of our economy. And so if we want to double our energy demand as we hit, $5 or $30 trillion, we are going to, if we continue the path that we are going to import a much, much larger amount of carbon atoms and burn all of them. And even today, by burning all that carbon, we are emitting about 3 billion tons of carbon dioxide in the air. This is not a great statistics to be proud of. We are the world's third largest emitter. Now, you'll often hear this term that on a per capita basis, our emissions are much lower than any of the developed nations, about 1/5 of what US emits on a per capita basis. But honestly, I don't agree with that, because our denominator is so large that anything you do per capita is a small number. So I think the quantum of emissions that we have is not something that we should be very proud of. So 3 billion tons of CO2 emissions today, and if we continue along this path, it is simply not tenable. And therefore, it is absolutely clear to all of us that if we want to reach that $30 trillion GDP, we must stop emissions, we must reduce emissions, and therefore use clean energy and also reduce imports. I think the two wars that have happened in the recent past have shown us that the more we depend on other things, the more unreliable things become, and our growth potential is hindered not by our internal competencies but by external factors, and that's something that is not the right thing to do. It's actually not negotiable, and therefore we have to look for energy options which are clean energy and options that make us more and more self-sufficient. This kind of narrative is happening across the world. Almost every country today is talking about, in their own jargon, Atmanirbhar. For good or bad reasons, this is what is happening today, and it is how the energy transition will evolve. So what options do we have as a country? The first and foremost is improve energy efficiencies, and I think India has done remarkable already in this area. I'm sure many of the lights across your campus have gone from CFL to LEDs, right? And that's a very simple transition. I remember when we were trying to buy the first LED lights, they were so expensive that we could not afford it. So it was actually ridiculous to replace CFL bulbs with LED bulbs. But within a span of just 3 years, the cost of LED lights came down so dramatically that they became cheaper than CFL. Right? And so this is an interesting lesson that the cost of something also depends on other factors, and one of them is the economies of scale. You start producing anything at very large scales, the cost starts to plummet down. So going from CFL to LED is just one example of how the efficiency improvement reduces carbon emissions. And almost every processes in industry, whether you are making steel or you are manufacturing a drug, if you improve your process efficiencies, there is a significant reduction of emissions that happens. And therefore, this is a low-hanging fruit, and a lot of effort is already happening in the country across the board, across all industry sectors, where improving efficiencies of everything that you do reduces emissions. So that's the first thing one must do. The second is improve renewable energy. And when we say renewable energy, we already think of solar, we think of wind, but we also think of biomass. And in fact, India has a huge amount of biomass. There's about 150 million tons of surplus agro-waste, biomass, agro-waste, which is collectible in this country. And when I say collectible, there is already supply chain. There are already people who collect after harvesting the biomass, they pelletize it, they stack it up, and you can actually go and buy it. And 150 million tons is not a small amount. If you were to use all of that biomass and convert it into electricity, you're already looking at about 20 gigawatts of electricity production. So these are the kind of renewable energy options other than solar and wind. None of these energy options are available, what we call RTC, round the clock, right? Some are seasonal, some are diurnal. Sun only shines 5-7 hours a day, which you can harness the energy from. Crops are seasonal. So all of these new options are variable, right? And we are so used to having coal or oil or gas, which is available 24/7. You just mine it and use it. We are so used to it that something which is a variable supply of energy becomes a very difficult prospect. Okay, but one has to live with it, and therefore, what is very, very important, equally important, perhaps even more important, is to be able to store the energy. You produce energy for some time during the day or some time during the year, and you got to store it so that you can use it round the clock. And therefore, energy storage options are becoming very important. And there are multiple options here today, and in fact, the one that India is betting big on is pumped hydro storage. I come from a region where we are surrounded with hills. One of the best pumped hydro storage project is very close to Pune, in a place called Satara, where you have a dam called the Koyna Dam, which is about 1,500 meters above the sea level. And from the bottom of that dam, we have tapped water. It runs down 1,500 meters down into a large cavern, where we have massive turbines that take the potential energy of the water and run the turbines and produce electricity. And when the demand for electricity comes down, which is when we are all sleeping, we don't need much electricity, producing more electricity, that excess electricity is used to pump the water back up 1,500 meters back in the dam. Okay, and so this is what is called pumped hydro, and it's a way of storing energy in the form of potential energy of water. Okay. And that's an option across the Western Ghats. This is an option that is explored, and now also in the Himalayan regions. What I'm going to talk about is the last option, which is hydrogen. Okay, and I'll tell you a little bit more about it, but this is also an option that is now looked at very aggressively to store energy. We have a lot of coal. We have very high ash coal, not great quality coal available in this country. And of course, we don't want to burn it, right? Because that is only going to produce more and more emissions. So what is today looked at, and this government is funding a lot of wonderful projects where coal is reacted with steam to form what is called synthetic gas. It's a mixture of carbon monoxide and hydrogen, a very potent and very reactive mixture. You use that mixture to run turbines to generate steam and therefore electricity, but you also then use it to produce chemicals. It's a great feedstock to produce a lot of standard chemicals that we use today. So this is another new technology that India is looking at, what is called coal gasification. And the last option is nuclear energy. And honestly, whether we like it or not, we really do not have an option of not using nuclear energy. I'll talk a little bit about it. So this is where we are today. We have about 85% of our energy comes from all kinds of carbon, which is fossil-based carbon, which emits these 3 billion tons of CO2. And this is where we want to go by 2050. 50% of the energy we should come from NFE is non-fossil energy, right? So this is renewable energy. And this is a very, very difficult task. And what is even more difficult is we have just 30 years to make that happen. In the entire history of human civilization, multiple energy transitions have happened, and they have taken more than 100 years. Roughly about 150 years to do any energy transition. We do not have that kind of time today. And so not only the scale of energy transition is difficult, but the speed at which we have to do the energy transition is an even more difficult task. Our Honorable Prime Minister has already announced in this historic meeting, COP26 in Paris, that we will become net zero by 2070. We will, in order to achieve that, we will install 500 gigawatts of non-fossil energy capacity by 2030. Today we are at about 170, so it's another massive 330 gigawatts to be installed within a span of only 6 years now. So all of these are very difficult things to achieve, but we got to do that. And if you look at whether that will be enough to make 40% of this, honestly they are not. And let me give you some numbers. If I take this 500 gigawatts of renewable energy and convert that into units of electricity. So when we pay our bills, we are charged per unit electricity, and per unit electricity is kilowatt hours, right? So if you multiply this with the number of hours in a year, which is 8,760, you will get a number of how many units of electricity will be generated with this number. Okay. Now solar, wind are not available 8,760 hours a year, but even if you say that you multiply 500 with that number, it only amounts to 40% of that. So only 40% of this pie here will come from that 500 gigawatts of renewable energy, right? So where is the rest going to come from? And many of us therefore think that India really does not have an option but to go nuclear. Okay, so we will see, I hope in the near future, a lot of more nuclear energy being used, and of course we have to deal with how what do we do with the nuclear fuel, the waste that comes out of it, and all those technologies are today available. We will have to deal with all of those problems. I'll come to this part where you look at what are the most carbon emitting industry sectors in the country today, and you will see that the power generation, which is all thermal power today, you burn coal and you make electricity, that emits the maximum amount of carbon. Then there is light transportation, all the bikes and the cars that we drive on the road. Agriculture uses a huge amount of electricity, and all of these can move more and more, or will have to move more and more towards these kind of non-fossil energy sources. So more of the electricity that is either produced or used will have to come from non-fossil based energies, and therefore this massive transition to battery vehicles, right, is happening because of this driver, in order to reduce that 5% contribution of emissions. But there are these two sectors where electrons are not enough, you need molecules. For example, if you go to a pharma industry, and this city is full of those kind of companies, they use hydrogen as a reducing agent. They use hydrogen for hydrogenation reactions, and huge quantities of it. If you go to a refinery, they use hydrogen to produce the best quality diesel that we all use today. If you go to a fertilizer plant, it uses hydrogen to produce ammonia and then to produce urea and all the fertilizers. Therefore, you need molecules in industry to be able to make those chemical transformations. You also need fuels to run very large vehicles, whether it is a truck or a bus or a ship or a train. You need fuels, and typically liquid fuels, to drive these heavy transportation and long distances. For both these applications is where we think electricity is not enough to decarbonize this sector, and therefore this is where we believe that hydrogen, if it is produced by ways where you do not emit carbon dioxide, and which is called green hydrogen. So you produce hydrogen without emitting carbon dioxide is a simple definition of green hydrogen. That kind of fuel is required, that kind of chemical feedstock is required to decarbonize these two very, very important sectors. Just to give you a number here, in India, for whatever reasons, 70% of cargo moves in India on roads, not by railways. It moves by roads, and therefore there is a huge amount of emission that is associated with all the trucks and buses that run across the length and breadth of the country. And that is where hydrogen starts becoming an interesting sector. And why is it interesting? Is because we call it a sector coupling energy vector. How does it couple? It takes any of these renewables, whether it is solar, wind, nuclear, anything, and you can convert those electrons into hydrogen by simply splitting water. So you take electricity, and this is school experiments that I'm sure all of us have done in schools. These experiments, you take water, you pass electricity through it, of course through electrodes, it splits into hydrogen and oxygen. So you take electricity, you take water, and you make hydrogen. This conversion process today is done at large scales, and it's a very efficient process. There's the equipment used for this is electrolyzers, and the best electrolyzers that are available today commercially are at least 75 to 78% efficient. Okay, and that's a great efficiency. Compare that to a diesel engine. You run a diesel engine in your cars or a petrol engine in your cars, it is at best 40% efficient. Okay, so the energy stored in diesel converted into energy that drives your vehicle, that conversion efficiency is only 40%, and this is the best diesel engine you can buy. This, on the other hand, is at least 75% efficient. So this is not a bad efficiency. This hydrogen, once produced, can be used in any of these sectors. So it is taking electrons from renewable sources and coupling it with multiple sectors, and that's why it's called a energy coupling vector. If required, this hydrogen can be reconverted back into electricity by again reacting those hydrogen and oxygen to produce water. Okay, and this is the reverse of this reaction, and this is called a device is called fuel cell, which takes hydrogen and oxygen, combines them electrochemically, not by burning it, but combining them electrochemically, and in the process you produce electricity. And even this is about 50% efficient today. Okay, so this is therefore a very interesting energy vector. Now, hydrogen is not new. We produce and use a lot of hydrogen today. In fact, India produces about 5 to 6 million tons of hydrogen today. And it is all used in refining, fertilizers and such kind of industries. But today it is produced by what is called a Gray process. That is, you take methane, you react it with steam in the presence of catalyst, high pressure, high temperature, and methane then reacts with water to produce hydrogen. But in the process, for every kilogram of hydrogen you produce, you emit 10 kilograms of CO2. Okay, so there's a huge emission that is associated with the production of that. So if you produce 5 million tons of hydrogen, you will emit 50 million tons of carbon dioxide. Okay, and therefore this is not anymore acceptable. We have to move this to more greener sources of hydrogen. There are many other sources of hydrogen. I will not go through all of them. I will go straight to this thing called the green hydrogen, which, as I said, is produced by water electrolysis. And if you do it by using green electricity, you will produce less than 0.1 kg of CO2 per kg of hydrogen. Compare that with 10 kg of CO2 per kg of hydrogen. And therefore, this is a green hydrogen production. It's called green because it just produces far less amount of CO2. If you look at other countries, they also are talking about what is called blue hydrogen. And blue hydrogen is actually quite simple. It sounds simple. You produce hydrogen by the same process, but whatever CO2 you produce in that as a byproduct, you capture that CO2 and you pump it down into oceans, into regions called saline aquifers, or you pump it in geological strata called basalt formations, and there the CO2 reacts there with minerals and forms carbonates. That is basically called sequestering CO2 in large scales in some kind of sedimentary formations. That process is happening in the US, in Europe, because there are actually fields available where large amount of CO2 can be sequestered. In India, we have the potential to sequester large amounts of CO2. In fact, if you pump CO2 down along the coast of India, 100 meters into the ocean, there are regions where you can store more than 34 billion tons of CO2. And remember, we emit only 3 billion tons of CO2 as of now, and that hopefully is going to come down year on year. It down, it's all extremely expensive. So for all these reasons, as a country, we have not invested in this technology. So as of today and in the foreseeable future, we do not have the capacity to take CO2 and store it in geological formations. The institute right next door to you, which is NGRI, has done quite a bit of work in understanding where are these formations where potentially CO2 can be trapped and preserved. However, we have not as a country invested in it. So while a lot of developed countries are looking at this as an option to produce hydrogen without emitting CO2, we cannot do that as of today, and therefore our government is betting on directly green hydrogen. And therefore, the country has come out with this roadmap called the National Green Hydrogen Mission. It was launched in the early part of this year, and it's about $2.2 billion program that turns to about 19,000 crores program. Much of it is incentivized for producing electrolyzers for water splitting, and therefore also for producing green hydrogen. There's a bit of money allocated for doing pilots and some money allocated for doing R&D. And I think CSIR, we feel very proud about it that the entire section of R&D, which is section 7 of the National Green Hydrogen Mission, was written along with CSIR. We contributed to it. In fact, the document talks about CSIR's contribution in that area as well. So this is a very interesting program, and I find it very interesting because this is the first time, at least in my lifetime, that India has taken a bet on a new clean energy vector for the first time into technologies which are not mature technologies. You think of solar. Till now we have never manufactured solar cells in this country. We manufacture panels. We import solar cells, we assemble them into panels, but we don't manufacture solar cells. You talk of lithium-ion batteries, sodium-ion batteries. This country does not have capacity to manufacture the batteries. We buy batteries and we build modules out of it. Okay? So we have never taken the bet of any clean energy vector in a large sense. And this is the first time where technologies are not mature anywhere in the world, and India is betting for the first time in these ambitious programs. I think we are in a very different kind of league now, where we are betting on these technologies. And therefore, the role of R&D institutions to develop technologies which are not mature, is becoming increasingly very important. Besides the mission document, there are also some interesting things that the government has done, and I call it enablers. So, for example, if I want to set up a water splitting machine, an electrolyzer on the east coast of India, where solar is not available to the extent as it is available, let's say, in Ladakh or in Rajasthan or in the run of Kutch. So I'm producing electrons on the west coast, but I want to produce hydrogen on the east coast. So I want to pump all those electrons through our national grid and bring them to Visakhapatnam, let's say. And that costs money, right? So to incentivize the production of green hydrogen, the government has started looking at incentives such as waiving the cost of transporting that much power required for the electrolyzers. And these things are temporary. These subsidies are temporary. This is just to accelerate the creation of these large electrolyzers in the country. And once they start running and they start producing hydrogen at scale, as I said earlier, like the LED example, you bring anything, you start manufacturing anything at scale, the cost starts to come down. So if you have large electrolyzers producing hydrogen at scale, the cost starts to plummet and slowly you remove the subsidy. So to begin this acceleration, this green electricity access to produce green hydrogen is a fantastic enabling mechanism. And I think we are fortunate to have something like a national grid. In fact, many developed countries do not have a national grid. Do you know that Australia does not have a national grid? If you want to go from the west coast to the east coast of Australia, there is nothing to transport electrons from here to there. Okay, there is no national grid in Australia for whatever reasons. India has a fantastic national grid. Of course, a lot of improvement in the grids are required to meet the fluctuations in the renewable energy, but at least we have a skeleton on which we can build on. And I think making use of this kind of infrastructure becomes very important strategically for India. Now, when I start talking about green hydrogen, people say, there have been so many hypes of green hydrogen. In the 70s, people started talking about hydrogen, and then it all died down, and it has happened multiple times. So why is hydrogen important today? Is it even important? Is it even likely to become important? And I think there are three reasons why hydrogen is important today. One, and why important, and why is it viable, right? One is the fact that climate change is now accepted as the fact that anthropogenic emissions in the last 150 years are real. Some leaders in the world still don't believe it, but this is real. There is enough scientific data to show that emissions in the last 150 years have caused a large increase in what is called the global surface temperature. So climate change is for real, and we need to decarbonize, and any decarbonization vector is going to be important, and hydrogen is one of them. Second is that the prices of renewable energy has plummeted like anything in the last decade. So here is the cost of silicon wafers just about 10 years ago, and this is where it is today. And therefore, the cost of electricity has come down significantly. In Pune, for example, if I buy grid electricity, I pay about 10 to 15 rupees a unit. If I buy solar electricity from people who generate solar power, I get at least 6 to 7 rupees a unit. Okay, so solar electricity costs have really come down very, very significantly. So to produce hydrogen by water electrolysis, you need solar power, you need wind power, and as the costs have plummeted, producing hydrogen becomes more and more viable. And the third reason is that the cost of the electrolyzers have also plummeted significantly over the last 10 years or so. So these are the three reasons why we believe that this time the hype around hydrogen is going to be real. And therefore, across the world, you will see a huge number of hydrogen projects have come up. About $300 billion of investments have been announced, and increasingly in India also we start seeing the announcements. So the National Green Hydrogen Mission talks about near-term uses of hydrogen, where all these 5 million tons, if replaced, will go in refining and fertilizer sector, and some of it will also be actually used to export. So from being a country that imports fossil carbon or fossil energy, we have an opportunity to start exporting clean energy to countries outside. And in fact, countries like South Korea, Japan are hungry for hydrogen, and we are so much closer to them. Today, hydrogen is shipped all the way from Australia to Japan. Instead of that, imagine shipping from Visakhapatnam to Japan. Okay? And there's a lot of talk happening between governments to make that kind of thing happen. In the midterm, by about 2040 or 45, this demand for hydrogen will double, will go to about 10 to 12 million tons of hydrogen, and a lot of that will start getting used into heavy duty transportation. And in the very long term, by about 2050, some of the sectors which are very difficult to decarbonize, okay, for example, steel industry, the size of a blast furnace is about the size of this auditorium and 3 times taller. It's a mammoth machine that takes iron ore and converts it into steel, and it emits huge amounts of CO2, right? Converting that into something which is, instead of coal for reducing iron ore, using hydrogen to reduce iron ore is a very, very difficult task. In fact, we are very proud that the first such experiment has already happened in India, where in a real blast furnace, real time, for about a week, coal was replaced with some amount of hydrogen, not complete hydrogen, but a significant amount of hydrogen, and the blast furnace was operated without any issues. But these are really difficult challenges, and they will take several years to decarbonize these hard to abate sectors such as steel and cement. So that's roughly the vision for how hydrogen will come in. And I just want to leave you with 2 thoughts, that beyond this, India has certain uniqueness where these kinds of energy vectors becomes important. There's along the east coast, again, the archipelago of Andaman Nicobar. We are looking as a country to develop this particular island, the Great Nicobar Island, which is very, very strategically located, just opposite Singapore actually, as a strategic island. You know, we are looking at developing ports, we are looking at developing renewable energy base there, and converting that into a shipping lane. This is already a high traffic shipping lane. Now imagine today Great Nicobar gets its energy from Chennai. You fill tankers with diesel, you ship it all the way to Nicobar and Andaman, and you fuel the energy needs of the island, which is perhaps the most ridiculous thing to do. So converting this into a green island where you produce renewable electricity, convert some of those electrons into hydrogen, and use those hydrogens to run ships across or convert them into methanol, ammonia, and so on. This is becoming a very strategic location. So these are unique opportunities for India to develop green hydrogen hubs there. The second interesting opportunity is this policy called the National Logistics Policy. And if you Google National Logistics Policy, this is one of its kind in anywhere in the world. And what they're looking at is, on an AI platform, you have an Amazon-like interface where as a user I say I want to ship X tons of goods from, say, Mumbai to Chennai, and the AI platform will tell me where it will go from, like a hub and spoke model. So from this port it will go to this warehouse, from this warehouse to that warehouse, and ultimately to Chennai. And what is the most optimal and the most cost-effective ways of transporting it? I can choose as a user. Do I want train transport, road transport? How will I do the last mile delivery and all of that? Okay, so it's a very, very unique platform. And what it will enable is transporting large amounts of goods over long distances much more efficiently. And so if you want to do this, hydrogen becomes an excellent option to run large trucks, like a 40-tonner truck, over a distance of 300 kilometers, 400 kilometers, right? It's a great clean energy vector to transport heavy-duty trucks over long distances. So things like these, coupled with the National Green Hydrogen Policy, suddenly becomes a game changer for the logistics, the transport logistics in India. So these opportunities are multifarious, and therefore many states are investing into it. Kerala has announced a lot of interesting projects on hydrogen, and many other states have done that. And we have also run many pilot projects on producing hydrogen and using hydrogen in the country. The private sector is also investing significantly in this area. Many companies have already announced projects for producing hydrogen, producing electrolyzers, and other such technologies. And in fact, the first PLI schemes, the incentivizing of manufacturing green hydrogen, the first tenders have already been announced. The bidders are already announced, and these are the first companies who will be producing that much amount of hydrogen in terms of megawatts. It's the measure of megawatts of hydrogen. For example, the Reliance electrolyzer will be 300 megawatts of electrolyzers, which will be producing 90,000 tons of hydrogen by water splitting per year. Okay, so just to give you a feel for what it means, if you want to make 5 million tons of hydrogen by water splitting, you will need electrolyzers of 30 gigawatts, okay, which is about 20% of that remaining 330 gigawatts that we need to install anyway. We need about 120 gigawatts of solar and wind put together. About 550 gigawatt hours of energy storage is required. So these are very huge numbers, right? About 0.1% of India's land mass will be required to produce that much solar and wind. $150 billion of investments, and these look very crazy numbers. But actually, on a country perspective, these are not crazy numbers. This is a tiny fraction of the energy budget today of India. So it's not very large from a country perspective. This is only 0.1% of India's land. You need 300 million liters of desalinated water to produce hydrogen, and you'll suddenly think, India is a water-starved country. What are you talking about? 300 million liters is a huge amount, but actually not. The city of Chennai today uses desalinated water for drinking, and Asia's largest desalination plant exists today, is running as I speak in Chennai, producing 100 million liters of desalinated water per day, right? So this is only 3 times that. So these numbers may look intimidating, but at a country perspective, they're not such large numbers, and this is a very doable thing. So 5 million tons of hydrogen produced by water electrolysis alone will reduce the emissions of CO2 by 30 to 40 million tons per annum, and a huge amount of savings of foreign forex and a lot of jobs that get created. I'm going to skip some of these slides. Each of these slides tell you about what is specific for India, which kind of electrolyzer is important, why is it important for India, and so on. I think I don't want to bore you with many of these details. All I want to say is that for since we are betting on a technology that is not mature globally, we have to start looking at what is India specific, what is important from an India perspective for each of these new technologies. And so some of these issues, points is what I've raised. I'll just touch upon digitalization. India has, all of us use mobile phones and we pay a pittance for it. But if you go to the US, you go to Europe, for the same amount of data, the cost of data is unbelievably high in those countries. Okay, we don't know how cheap data is in India today. And I think that is great for technologies like this, because all of these electrolyzers, imagine they're running on an AI platform which is controlling the efficiency of the electrolyzer every second, which is all possible today by simple digitalization. Okay, you have IoT, you have AI platform that controls processes on a real-time basis. It also predicts. For example, it will predict how much electricity is going to be available tomorrow or a week from now, based on all the historical data that is available, right? And so we can plan for all of that based on these kinds of very sophisticated digitalized platform. And because the cost of data is so low, it becomes very viable for us to do that. So digitalization coupling with new technologies like hydrogen generation is a very unique thing that India can do even today. Okay, a lot of talk happens about, is all that hydrogen cheap enough? Is it viable enough? Is it economically viable enough? We think that if you take an electrolyzer and integrate it with a solar plant and you design it properly, hydrogen today can be produced even today at about $3 a kg, okay, for this kind of thing. And most of the large companies who are betting on the PLI scheme are actually planning to design their electrolyzers in such a way. So it's an integrated plant where you have a large solar field with an electrolyzer sitting next door to it. And that can produce hydrogen at about $3 per kg. If you have the waivers of electricity transport, as I said, you can produce hydrogen in Gujarat or Rajasthan, electricity there, and pump electrons to Tamil Nadu or Andhra and produce hydrogen there. If required, that is even possible today. And as the technology matures, these costs start to come down. If you bring in large-scale manufacturing, the cost starts to come down. And we are looking at a magical number of about $2 or less than $2 per kg. If hydrogen hits $2 per kg or less than $2 per kg, it's a no-brainer. This is the energy vector which will make anything very, very viable today. So we are not very far away even today. $3 is achievable, and target is to go below $2 a kg. And these are some of the ways by which we can go from $3 to $2 per kg. Okay, this is what is called the levelized LCA. The carbon emission calculations, actually, what is called the life cycle analysis. And if you look at just solar to hydrogen, as I said, it's less than 0.1 kg of CO2 emitted per kg of hydrogen produced. If you look at solar plus 5% of grid, which is carbon based, you can see how less than 0.1 becomes suddenly 5 kg of CO2 per kg of hydrogen produced. So grid has so much carbon intensity to it, okay, that even 5% of grid takes the emissions significantly higher. Now India has declared that anything less than 2 kg of CO2 per kg of hydrogen will be defined as green. Okay, so even 5% grid is not enough to get green hydrogen. we can only go to about 1% grid injection. So therefore, all the hydrogen that will be produced must necessarily come from either pure solar or some combination of solar and wind. And that's how the whole country is planning to produce green hydrogen. The other thing that is coming up for hydrogen production is biomass. And I said earlier that we have about 150 million tons of biomass available today, waste biomass. And instead of burning it and causing all the pollution in the northern parts of India, if you can take that, gasify it, and convert that into hydrogen, it becomes a very potent source of hydrogen. In fact, the person who is really leading this is Professor Dasappa from Indian Institute of Science. He has a wonderful process for converting any kind of biomass into hydrogen. And he tells me that the potential for producing hydrogen today from that 150 million tons, if all of that 150 million tons is used to produce hydrogen, we can easily make today 1 million tons of hydrogen. So 20% of what is the country's demand for hydrogen can come only from biomass. And in the process, you produce very nice carbon called biochar, which can be used to improve the quality of soil, as not as a fertilizer, but just improving the porosity of the soil, reducing the acidity of the soil, which has all happened because of rampant use of fertilizers, insecticides, pesticides. Our soil quality has really deteriorated. Putting biochar in the soil to an extent improves the quality of that soil. So these kinds of technologies today are happening in our institutes, and there is a great opportunity for taking these technologies from labs all the way to commercialization. And this happens only when the country bets on new technologies at a time when the technologies are not mature. So we are not simply importing technologies, we are not simply licensing technologies, we are developing technologies in our labs, scaling them up and commercializing them. So this is a great opportunity for us. Right here in IICT, there is a very nice plant, a pilot plant that produces biohydrogen. It's green hydrogen coming from biosource. So it's a process called dark fermentation, where you do acidogenesis by a consortium of bacterium. And if you take any kind of sugars, you can do glucose of course, but you can take biomass. You can, through the dark fermentation route, produce hydrogen and produce CO2. And that CO2, through another set of consortium or through algal ponds, can further capture that CO2 and convert them into methane. So right here in IICT, there's a plant right here that produces not only hydrogen but also methane, and also a very good amount of algal biomass. Okay? So it's an interesting technology, again, developed in the lab with a great potential to scale up and commercialize. There are other opportunities such as bagasse. We produce a lot of sugarcane in the country, and all that bagasse today is simply burnt to produce electricity. But instead of burning it, which is the lowest value use of it, you can use it to produce hydrogen by multiple technologies. It's a very interesting way to produce hydrogen. And these are technologies that are not available to license commercially from anywhere in the world. You have to develop them. You have the opportunity to develop them in the lab and commercialize it. I think I will skip some of these. This is about transportation of hydrogen over long distances through compressed hydrogen cylinders. There is a lot of work happening today in IIT Kharagpur, for example, to produce carbon fiber cylinders which can store hydrogen at as much as 700 bar pressure, 700 times the atmospheric pressure. A lot of work required to commercialize this technology, but there's a lot of advance that has already happened. Right, I'll skip some of these. I just want to focus only on the last thing. There's a use of hydrogen, as I said, in refining fertilizers, in making steel, but this is one sector where again there is a very specific India advantage here. And again, I refer to Hyderabad as a city where you produce a lot of these chemicals. pharma. This is the pharma hub of the country, right? A lot of pharmaceutical companies, and they all use hydrogen today. The amount of hydrogen used in pharma plus agrochemical sector is of the order of 100 kilotons per annum. 100,000 tons per annum is the amount of hydrogen that is used today. All of that hydrogen today is gray hydrogen. It emits CO2 along with it. Imagine converting that into green hydrogen. This entire sector can be decarbonized. And decarbonizing this sector is very critical for India because these chemicals are exported outside. 22% of North America's drugs come from India. So you are actually selling outside in the markets, not in Indian markets, in markets outside. And in those markets, the pressure for decarbonization is very, very significant. Companies have to get certifications which are very, very stringent, saying that their processes for making the drugs are now getting decarbonized. And therefore, an easy way to decarbonize is to switch from gray hydrogen to green hydrogen. And therefore, we are working with a lot of companies here in Hyderabad, switching the hydrogen from gray to green. I will skip that, but just want to focus on this. We hope to create the first hydrogen valley in India in a place called Kurkum, which is about 70 kilometers from Pune, where we have these kinds of fine and specialty chemical. This is a demo, a pilot experiment to show that this can actually be done. So this is a company, there are 3 companies here which are producing pharma intermediates and some aromatic compounds and exporting them. And they produce hydrogen today by a gray process which emits CO2, and we are telling them we will give you green hydrogen produced either by water electrolysis or by a very novel bioethanol route. They, along with us, we're setting up a project of about 100 crores, of which 70 crores is coming from industry, 30 crores coming from DST, and we hope that we'll be the first in the world, first in India, to look at setting up how hydrogen valleys are created, where you produce hydrogen, you store hydrogen, you transport hydrogen, and use hydrogen in this very interesting sector. These are our industry partners, and I hope that the results for this are likely to come out by the end of the month. We are very hopeful to get the opportunity to create the first valley of hydrogen in India. So I'll summarize. I'll not read out all of this. I'll leave it here. I know I have probably exceeded my time. Happy to answer any questions if you have.
Fantastic talk, Ashish. So the transmission losses, particularly if you talk about the national grid. So we know that there's a loss, huge amount of loss.
Yeah.
And how much of investment is happening to create micro, systems where you reduce the transmission losses, the density of, hydrogen to be used for transportation. You did mention about the fiber thing, but that also is a big sector that needs to be boosted up. Unless you take care of these two, to me at least, you are the expert, these becomes more obvious challenges to putting this together at a national level.
I fully 100% agree with you. While I did say a lot of positivity that the grid exists in the country, it has to be smartened. The grid has to become much more smart, and increasingly so because of the variability of renewable energy power. And the losses are, a lot of it is associated with the way the grid operates. So you make it more smart, you can significantly reduce the loss today. The losses are very high today. Even in the US, the losses are 5%. In India, we are looking at 15 to 18% loss. So that's very significant losses. But it's just because the grid is not as smart as it can be. And again, I say that with the digitalization that is possible today, it is not, investments will be required, but it's not such a challenge, technologically speaking, to make the grid smarter. Now, the government has already started taking steps in this direction. For example, the local infrastructure, the local transformers, huge numbers have been replaced in just the last 3 years. I know several companies who have been who have won these kinds of bids to do local refurbishments of infrastructure, essentially the transformers, the substations, and so on. And the new ones coming in are far better technologies. They're much more modern technologies. And so you have to build ground up. The local infrastructure has to be made more strengthened, made more technologically competent, and then it's easier to connect them with a smarter grid. You can't just have a smarter grid with old technologies at the local level. So I think there's a serious effort going on to electrify. Much of this is actually driven by railways, because the railways is now almost 90+% electrified. So to run Indian Railways on purely electricity basis, has forced us to upgrade our infrastructure. Okay, and that has sort of there's a windfall effect. It has percolated to local districts and talukas and so on. So I think with that, there will be significant improvements in the reduction of transmission losses. That will only enable this, right? So that's the hope. The second question is even more relevant: microgrids, right? And I think again a lot of work happening in the microgrids area. I know one in here in Andhra eastern coast, where microgrids are one large microgrid is being set up. There are some also happening in northern India, foothills. So we'll see how the local grids, microgrids develop. That's a little difficult to do, because you have to have multiple renewable sources of electricity which you have to combine together for the local sector. So national grid, I think I'll know a little bit more about what is happening at the national levels. Smaller microgrids, I don't know enough about how many are being developed. Yes, sir.
Thank you.
Ashish, I have two questions. OSHA is actually investing into synthetic gasoline, and German government actually invested a lot of money in that.
Into what? Sorry.
Synthetic gasoline.
Yeah.
Capturing the carbon dioxide from the environment, they're actually creating synthetic gasoline. Currently, it's costing about twice as much, but they believe scale up obviously would bring the cost down. How do you see that affecting the overall process and the overall process of the green culture that's currently in the vogue? The second part is, there are several technologies that actually people are investing into. Like you mentioned, you have lithium, you have sodium, you have hydrogen. So in terms of ROI for these technologies, it's a hard sell. So how do you see that happening? Do you see the infrastructure actually paying off in the long run? So which one do you think will pay out the most?
Both difficult questions. So the first one is about liquid fuels, I would say, right? Synthetic gasoline, liquid fuels. I honestly think that there is no better battery than liquid fuel. The energy density of liquid fuels is so high, nothing else competes with it, right? So if you are moving very large vehicles, there is nothing better than liquid fuel, which we are using today, except that it is not green fuel, right? Gasoline, diesel, none of that is green today. But if that can be green, it makes a big difference. So that's why SAF, aviation fuel, sustainable aviation fuel, biodiesel, okay, are two interesting energy vectors that from an India perspective, there has to be a significant push given to it. Synthetic gasoline is a Fischer-Tropsch process. You gasify coal, you gasify biomass, make syngas, and you do Fischer-Tropsch synthesis to liquefy, to make synthetic gasoline. That technology has been around for a long time, but it has not been scaled to a point where the costs have plummeted. And the Fischer-Tropsch is not the problem; it's the capture of CO2 that is the biggest problem, right? It's still not viable, and I don't see how soon it can become viable, because the cost of capturing CO2 is still excess of $130 a ton. At that price point, synthetic gasoline doesn't make sense, but aviation fuel does. and biodiesel does. Right? So those liquid fuels compared to synthetic gasoline is what I would say the country is betting on, and you can see that already happening. The air industry is already signed up in India on this particular global certification program called CORSIA 28, which means by 2028 we cannot fly. I think 50% of our aviation fuel has to become green. We have signed already on it, and therefore we don't have much time left to convert to start using green sustainable fuels, SAF, and therefore you will see a lot of plants coming for SAF, a lot of industry starting to produce SAF. IOCL, Praj, they have already started to produce SAF. And many airlines have also moved and they have tested. Our own lab in Dehradun has all the technology to make SAF, and they've already flown commercial as well as military aircrafts purely on SAF basis. So I think these are low-hanging fruits where compared to synthetic diesel, synthetic gasoline. The second question was about batteries and fuel, comparison of the two.
ROI.
The jury is not out yet, right? And I don't know how it will evolve. All I can say is that different countries will deploy different solutions, and there will be no one solution that is uniformly used across the globe, which is again very different than what we are used to. Today everybody is using gasoline, everybody in the world uses diesel, but that is not how it will pan out in the future. One country may bet for batteries, another country may bet on hydrogen. So depending on the local supply, depending on the local environment, each country will adopt its own green fuel. The jury is not out yet. Whether India will have battery vehicles or hydrogen vehicles, I don't think we have to wait and watch. I am very prejudiced on hydrogen, so I'll say yes, it will be hydrogen, but I will be wrong by saying that.
Yes, Raghu.
Dr. Lele,
Yeah.
Thank you for that wonderful talk. So we seem to be focusing a lot on carbon dioxide, but my understanding is that methane is a bigger problem in terms of temperature increase, and then I also understand that a lot of methane comes from cattle. Are there technologies to be able to trap this methane and work on something like this?
Yeah, great question, because methane has at least 30 times the potential for greenhouse effect compared to CO2, and so methane leakages is a global problem. We don't mine methane, if I've used that word. We don't extract methane from earth. We don't have too many fields. Again, KGD6, the Krishna Godavari basin, is perhaps the biggest source for methane, where we dig out methane. When methane comes out of the mines and is captured, trapped and transported, there are many leaks there. If methane is imported, such as what we do in the form of liquefied natural gas, there are stations where it is gasified again and pumped into our gas grid. There are leakages there, and trapping those leakages is the most important thing that is happening even today. So there is a regulation for all private players, including those who operate the gasifying stations, such as one in Hazira, one in Visakhapatnam. There are regulations there where they have to minimize the methane leakages. They have to first measure and then minimize. The second problem that you rightly mentioned is cattle, and India has large livestock, I think the largest in the world. Nothing is happening honestly in that area yet. Okay, we do not know how much methane is emitted from that source, and it's very difficult to also do anything about it because it's a dispersed emission of methane. There are a few technologies available. For example, our CSM CRI has developed a feed which can be mixed with whatever feed you give to cattle, mostly hay or green. You mix with it, and it affects the gut microbia to reduce the methane emissions. That is the claim. But it is not very widely used still. So the measurement, whether it is methane leakages coming out of mines or whether it is methane leakages coming out of livestock, we really have no measure of it. And that is the first problem. If we don't measure it, we don't know how much we are emitting, right? First measure and then see what you can do to reduce that. But the first step itself is not known yet. So it's a problem, it's a live problem, and nothing much has happened there.
Yeah.
Yes.
Government is encouraging, this side. Government is encouraging a lot of solar energy now. So how much solar energy can be produced in next 5 to 10 years, and how much hydrogen energy can become? Because these two energy will have great help. And then in that situation, when the day will come, we will stop the import from oil from the Middle East.
So solar potential that is mapped for the country is 475 gigawatts. So the target of 500 gigawatts that we talk about will mostly be solar, but there will be some amount of wind also that is coming in. So 500 gigawatts is the target till 2030. And as I said, we are about 170 gigawatts today. So there is another 330 to be added. So that's where the action is happening. How fast can we get to that 500 gigawatt number? Mostly solar. And while we say Atmanirbhar and so on, we import a large amount of solar cells from our very friendly neighbor. It is the reality of life. But the first solar cell manufacturing plant in India is likely to come up by the end of the year. Okay, so we will start manufacturing solar cells, silicon and solar cells, so wafers, polysilicon wafers, and the first heterojunction solar cells will also be manufactured totally in the country. So hopefully there will be reduction in the imports that we get. So to answer your question, 500 gigawatts is the target. Of that, 330 is what we need to establish by 2030. Right now, a lot of imports. But by the end of the year, we hope to have the first actual manufacturing of solar cells happening in the country. So that's where the country is headed. And to produce the first 5 million tons, as I said, we need 120 gigawatts of that energy. So of the 330 that we'll set up and the total 500 gigawatts, 120 will be required for producing hydrogen. So it's doable. It's not a problem that is unsolvable.
Like green hydrogen, they are here.
Yeah.
Like green hydrogen, green methanol is also a talk of the town. So how do they compare in terms of storage, energy efficiency and productivity? Green methanol and green hydrogen. And can methanol be used as a biofuel as studies are proposing?
Yeah. So Niti Aayog has a map, a roadmap for green methanol. Today, more than 95% of methanol that is used in the country is imported. Okay, it's coming from Qatar, Iran, and some from China. So it's all imported today. There isn't yet a plan that I see for substituting all that imports of methanol. But Niti Aayog is talking about green methanol, which is basically coming from the gasification route. So if Indian coal can be successfully gasified, and gasification, as I said, is the process where you react coal with steam to produce syngas, a mixture of CO and hydrogen, then it's very simple. Syngas to methanol is one-step catalytic process, which is a very well-known technology. So it's not the production of methanol, it's the gasification of coal that is the challenge, especially for the high ash coal of India. And there are at least 4 pilot plants today working at different places for gasification of high ash coal. The other is gasification of biomass, and I told about Dasapa's work where biomass can also be gasified to give you the same thing. So methanol is doable. Is it viable? As of now, unless you bring scale to gasification, it is not viable. Today methanol price I think is about 30 rupees a kg. It has to go to about 20-22 rupees a kg to make it really viable. Okay. So unless scale comes in, we really cannot see the future for green methanol. But it's also touted as a good source for hydrogen carrier. So you convert hydrogen into methanol and reconvert back to hydrogen.
One last question.
So, wonderful talk. So, one of the concerns that I have is the raw material that you're using for your electrolysis is basically desalinated water. So, one is it's an energy intensive process to desalinate water, and secondly, there's an environmental cost that comes with it with the salinated water that you are basically getting as an extra. So, what are the measures that are being taken to mitigate both of these? One is the energy and the cost factor for generating that, and secondly, the
a great question. So interestingly, if you look at what is the contribution of the water desalination cost to the hydrogen cost, okay, it's less than 7%. So yes, desalination requires energy, but not as much as we think, so its cost contribution to hydrogen is not very significant. So that is not so much of a problem, but environmental problem is definitely there. And there are only two ways to solve it. One is whatever brine comes out of the desalination unit can't be just dumped in the ocean nearby, but you have to take the pipe deep in the ocean. Okay, there if you release it, it very quickly dilutes out. Okay, and then it is okay. But if you dump it near the coast, you can get algal plumes coming out there, and that has happened. So now there are regulations that if you can't dump it deep in the ocean, then you have to treat it before you can release the water out there. So there are technologies where you actually, very interesting technologies where you take CO2, either you capture from air or you have a point source such as a nearby steel plant or a refining plant where CO2 is available. Today it is emitted. But you take the brine from desalinated plant and you take CO2 and you mineralize it, because the brine contains a lot of divalent, trivalent, calcium, magnesium, strontium, a lot of these ions. So they are great to react with CO2 and mineralize. So you capture CO2 also and you remove the salinity of the brine, right? So it costs, nothing is free, but because of environmental pressures, you have no alternative, you have to do it. So these are the two options. There are two plants, one of IOCL and one of Reliance on the west coast of India. Both of them pump these brine deep inside the ocean. And there's a cost for doing that, but they do it. But the smaller ones, such as the Mangalore refinery, for example, has to treat water and then only release it in the ocean. So, but at least there are regulatory pressures to do that.
Thank you, Dr. Lele, for this incredible talk with valuable insights. To honor and express our gratitude, I would like to invite our director to join us on the stage to felicitate Dr. Ashish. Thank you, Dr. Ashish and Dr. Vinay. We've had an enriching first half of our Founders' Day celebrations, filled with insightful talks and engaging interactions. Now it's time for a well-deserved lunch break. Please recharge for the second half of our festivities. Please be sure to join us back here at 2:45 p.m. as we resume our celebrations with more exciting presentations and activities. Thank you.